I'm going to be talking about something that a lot of us probably encounter regularly, and that's really working with very large data sets or big data. And so by way of introduction, I'm going to put this up, and I think most everyone has probably seen this. This is the forecast cone for currently tropical storm, probably soon to be Hurricane Barry. So if you're going to be traveling through Louisiana, you might want to pay attention to this. And these are very important forecasts because a lot of people live in the region covered by that forecast cone, and the cone represents kind of an uncertainty of where the storm will go. And so we need accurate forecasts of tracks of large and powerful storms such as hurricanes. And so one thing you probably haven't seen is this, and this is a plot of all of the different model forecasts of the track of Hurricane or Tropical Storm Barry. And there's a lot of variation in that, but what I really want to point out is just how many models there are, and these are not even all of the models or all of the ways to view the model data that we have. And so what we're really working with is a big data problem. We have lots of multi-dimensional data sets with total sizes that can be several or even many terabytes of data. And so we need to be able to process and subset these data sets efficiently. And one way that a large data set can be used is for something similar to a pattern matching that can help you improve a forecast. And so what we're looking for are two states of the atmosphere which resemble each other rather closely, and that's often referred to as an analog in atmospheric science. And so analogs are really a statistically similar state of the atmosphere. You use a statistical comparison between the current atmosphere and look for something similar in a data set. And so we're talking about multidimensional numerical forecasts with large data sets containing 300 or more unique possible analogs. You also usually use multiple predictor variables, and so that further increases both the size of the data set and the number of computations that are required. And so raw data set sizes can exceed 150 terabytes, and this needs to be efficiently processed and subset and post-processed in order to make any sense at all of this kind of large data set. So I'm going to talk a little bit about an example of working with such a large data set that's come from some of the work I've done over the past couple of years at Texas Tech. And so I have a data set compiled of a one-year data set of forecasts from the weather research and forecasting model that's been mentioned a few times in other talks. And I won't go into depth of what this model actually is, but you get four-dimensional forecasts in space and time of the atmospheric pattern, and you have high spatial and temporal resolution, usually covering a domain around the size of the continental United States. And so my total data set size was about 156 terabytes after I generated the data before I began processing it. And so we really need to pare that down because that's just too much data to really get anything meaningful out of. And so the first thing that you really want to do is to post-process the data set in some way to make it more usable. There's a lot of variables that are output in a forecast like a WRF forecast, and you may not necessarily care about everything that it outputs. Plus, as was mentioned in other talks, the output of an atmospheric model is often on a staggered grid, and that's not necessarily useful for scientific analysis until it's been destaggered and put on a common grid. So by post-processing, we can reduce the total data set size, in this case by 96%, and further simplify the subsequent scientific computations simply because the initial raw data is on an irregular vertical grid and a staggered horizontal grid, and by interpolating that to something more usable, it makes our life a lot simpler in the programming. And so the desired format of the post-processed data really should be something that has a regular grid and is in a multi-dimensional array format. NetCDF works fairly well for this, especially if you're in a traditional high-performance computing environment, though it may be less useful in cloud environments. Adding metadata and making things CF compliant, at least enough to use Xarray makes things a lot easier as well. And so that's what I did in this project, and everything that I wrote in terms of scientific computation leveraged the indexing and computation backend in Xarray. And that's not really required, but I would encourage everyone who's working with large data sets, even small data sets, to start using Xarray because it really simplifies the code and the indexing that you're going to do later. So I'm not going to go any more into post-processing, but I will direct you to those two links if you want to see some specifics of how I've done it, or if you are working with the WRF model yourself and would like some code that may help you out. I will say that when you're doing post-processing, use existing community-supported packages. There are a number available just for the type of data that I've been working with. And so I'll give a shout out to WRF Python and MetPy and the CFGRIB integration into Xarray, as those really helped me out to make this work better. So now I've got a data set that's on the order of about 6 terabytes, which is a pretty nice reduction because that's a 96% reduction in our disk usage. And these have been split into individual files, and so we have about 10 to 20 gigabytes that would need to be held in memory for analog searching. And that's kind of large, and so one thing we can do on that is to use Dask's chunking to load pieces of the data into memory at a time. Now that's where we get to kind of the hard part. Because if we've got a large data set, we want a search that will allow us to search along a single dimension for slices that are similar in other dimensions. What does that mean? Well, if we've got 4-dimensional data, we might want to look in the time dimension and match it to something that is 3-dimensional in the spatial dimensions. And so that means we have vectorized operations, but there's a lot of data involved in that, and we want to simplify it, make it fast, and make it not use too much memory. Another thing we want to do is leverage existing libraries for data handling and computations. I simply, as a graduate student, don't have time to rewrite all that code myself, so I want to use as much that already exists as possible. Another thing that's really useful is to design code that uses data-based indexing. And what that means is if I have a coordinate array that represents all the time steps in my data, I might want to use actual time values, like a pandas timestamp, instead of index values to subset my data set. And then also, it's possible to intelligently index the data based on some initial calculation. I'll talk about this a little bit more, but that means that I can subset data down on a case-by-case basis and reduce how much data I'm making calculations on without making my code less flexible. And then we want it to be flexible for a lot of cases and multiple variable types. And above all, we want this to be efficient so that it doesn't take too long when we go to run it. And so if we're going to just do pattern matching, that's not very difficult. We can do a minimization of RMSE between the pattern we care about and all of the possible matches. And we would probably do that along the time dimension. And that's pretty simple to do in NumPy. You can write a little function that calculates RMSE, and then you can minimize that, applying it along the spatial dimensions, and find out which time corresponds to the smallest RMSE. But that doesn't work so well with large arrays. And we're looking at arrays that are 270 by 321 in the spatial dimensions. So that gives us over 86,000 points for our initial reference array. We might have as many as 3 variables that we want to compare and 365 different times that we would want to compare to. So ultimately, we're looking at over 100 million points for our final calculation. That's a lot of points and can easily overwhelm RAM, especially on smaller systems. And so that is where we start to look to use Xarray. We can use Xarray to do our subsetting out of memory so that we don't have to perform computations on that entire grid, especially the spatial grid. And then we can use Dask to load these arrays in chunks that are going to fit more easily into memory. It's actually quite simple to set up Xarray to use the Dask chunking. It's simply an extra argument when you go to open the data set, and you just supply the chunks argument and a dictionary corresponding to what the dimension names are and how many chunks you want in those dimensions, or how big you want the chunks to be. And then you can do some additional subsetting by selecting just specific variables or a specific time. And I'll note that we're using the data-based subsetting and indexing, so I don't have to give it a specific index value for the time dimension, but rather I can give it a pandas timestamp corresponding to the actual time that I want. Simplifies the code, makes it easier to get exactly the data you're looking for and not make mistakes that you don't know about. Another thing that we can do is subset based on some initial calculations, or in my case, defined threshold. And so Xarray holds a lot of the attribute data or all of the attribute data in a dictionary, and that's a dictionary that you can add values to. So I added my own threshold to the attributes, which I can then pull out later and index the data based on where a smoothed version of the data is greater than that mask. And then by dropping all of the points that don't meet that, I end up reducing the number of points for my computation by a very large amount. I mean, it could be somewhere between 10 and 15 points to as many as 100 points, a few hundred points, but nowhere near the size of performing a calculation on the entire grid. Can we go faster? If that's not fast enough for you, because this is still a serial calculation, we can start applying Dask. And so one thing that has been mentioned in other talks is the use of the Dask delayed option. And that's actually a pretty simple decorator to implement around your function. So here we have the same RMSE function that I showed earlier. We've now wrapped this Dask.delayed wrapper around it. And if we had multiple variables that we wanted to calculate RMSE for, we could set up all of those calculations in a loop and append each object to a list, and then let Dask compute the objects in parallel at one time. I found that this resulted for my code in about a 10% speed up simply by doing that on one function and not even optimizing the rest of the code. And so the optimized code then that I created ends up giving us an analog search in approximately 3 minutes, which is pretty reasonable considering that we were running this at the beginning of a WRF model forecast, which would take about 6 to 8 hours to run. So it's almost negligible relative to the time to run the model itself. Now, it's not really quite as easy as what I showed you, because this is a very overview talk in nature. There's a couple of challenges that you can start to run into when trying to implement something like this with Dask. It's really easy to split the data using chunks in Dask, but it doesn't really increase the speed of the code. It just keeps it from overflowing the memory and crashing the system, which is fine if you have a small system and you just need the calculations to be done, but on a high performance system, it really doesn't make the code more efficient. It significantly can reduce the performance unless you also implement parallel processing. And that parallel processing requires a decent amount of configuration, and the documentation is somewhat limited and specific to specific systems. And so we have not yet really been able to implement parallel processing on TTU systems. We're working on it. It's just a challenge that we have been busy with other things lately. So in short, Xarray and Dask provide a really powerful computational tool, but there's a pretty steep learning curve, especially when you first start to learn the indexing in Xarray and a lot of the chunking and parallel processing in Dask. So a quick summary, large data sets like this really require some efficient analysis code design. We need to do processing and subsetting to increase efficiency and reduce the code complexity. And doing subsetting out of memory in Xarray and delaying the computations using Dask delayed does help to increase the speed and keep the memory from becoming so large that it overwhelms the system. Serial computations in memory without chunking is still the simplest to implement in my opinion and in my experience. It runs relatively quickly if you have enough RAM for it, which I did. But if you don't and have to start chunking, you're going to see some serious slowdowns. So parallel processing should help with that, but it's kind of difficult to implement. And I think we could use some additional documentation on how to do that on multiple systems and different kinds of systems. So further improvements in the Dask integration in Xarray, though, will really continue to enhance big data analysis in the geosciences. There's a lot of challenges when it comes to trying to do multidimensional numerical modeling work, and Xarray and Dask really have been useful for that, and I think will continue to be a great tool in the geosciences. And so if you're interested in more information on this and some of the more nitty-gritty details of how I designed this project, you can see that GitHub link, and with that I will take some questions. Thank you.
So do we have any questions for Tyler in the audience? Yeah.
Good, Doug. I'm curious, you mentioned that you add your own thresholds in after you slice your data set and you have the 1 million points. To make that smaller, you add thresholds to your attribute dictionaries. How do you decide, isn't that manipulating the data too much?
Yes and no. In this case, it's not, because that's a fairly common practice for the type of research I was doing. Yeah, you would want to be careful about not just getting rid of data that might still be important. In my case, it generally was being done on a precipitation data, and so the threshold really just gets rid of all the points where there's no precipitation at all and retains the points where there's something interesting going on.
Hi, thank you. Have you run into issues with Dask maintaining your Xarray coordinates during processing? And if so, how did you solve that problem?
I don't think I've had any issues with that. I've had a little bit of trouble just being able to use Dask at all. So I'm not sure I've gotten far enough into it to really be able to answer that fully.
Do you have any recommendations for the type of documentation you would like to see? I work with completely different data than you, but have run into similar problems of kind of stumbling through getting my chunked data parallelized.
Yeah, I think one thing that would be helpful would be to have some more examples that if you could run this code and see this particular type of output or this visualization in the bokeh display, then this would be what you would expect to see in order to know that you've actually got it working. Because some of it is a server-side configuration issue, and some of it is a user-side, like actually using the correct Dask functions in the correct places. So I'd love to see a little bit more detailed examples, and then also some that are specific to high-performance computing systems rather than cloud computing.
Any other questions for Tyler? No? Okay, well, thanks so much. Oh, sorry.
I just have a comment. There's going to be an Xarray sprint on Saturday, and a big focus of that is just helping to onboard new users, not necessarily working with the library. So a lot of focus on docs and examples. So many of those things that were just raised, we could actually all work on together on Saturday if you're going to be at the sprint.
Great. Thanks so much.
Thank you.